Hello, I'm Nazia, second year ECE student from GPLI College of Engineering and Technology. Today, I'm very happy to present my internship experience and the project that I completed during my internship at Emertxe Information Technologies. Before I begin my presentation, I would like to thank my guide, Lakshman Daniel ma'am, for their continuous support, valuable suggestion, and encouragement throughout the internship. Their guidance helped me understand embedded systems and successfully complete my project. During this internship, I gained practical knowledge about embedded systems, STM32 microcontrollers, embedded C programming, and real time project development. And now, let's start my presentation. First, about the internship. This internship was conducted by Emertxe Information Technologies, which is a well-known training organization specializing in embedded systems. The main objective of this internship was to provide industry-oriented practical training rather than theoretical concepts. Throughout the internship, I learned various embedded technologies through the assignments, coding exercises, simulation, and with the final project. The training covered embedded C programming and also microcontroller programming, STM32 microcontroller, peripheral interfacing, debugging, simulation, and the project development. One of the most valuable aspects of these internship was the hands-on learning approach, where every concept was implemented practically. This helped me understand how embedded software is developed and tested in real world applications. Overall, this internship was a valuable learning experience that strengthened my technical knowledge and also my professional skills. The next, the objectives of this internship. The internship has several the important objectives. The objectives was to understand the fundamentals of embedded systems and also along with their applications. And also was to improve programming skills using the embedded C language. And also was to learn STM32 microcontroller programming and understand how different peripherals such as GPIO, ADC, timer, and UART work together. The internship also aimed to improve debugging skills, project development skills, and problem solving skills. So the internship outcome it's again a complete knowledge of embedded system development process from coding to testing. Finally, the objectives was to provide practical industry experience by developing a real-time embedded project that integrates hardware and also the software. The next, the technologies I learned during this internship, I the important technologies that are widely used in the embedded industry. I learned embedded C programming, which is the basic programming languages used in microcontrollers. I learned STM32 microcontroller programming using STM32 Cube ID. I also learned GPIO programming, general purpose input and output, ADC interfacing for reading analog values, and the UART communication for serial data transfer, a timer programming, interrupt handling, and also the debugging techniques. Apart from embedded programming, I also learned a Python program to develop GUI, a graphical dashboard for displaying real-time vehicle data. Another important technology I learned was a Picsimlab, which helped me simulate hardware without requiring a physical development board. I used these two famous tools, System30 and Picsimlab, in my entire internship, and also programming skills. The difference between microcontroller and also the microprocessors. Overall, the internship improved both my programming knowledge and practical implementation skills, and also the STM32 Cube ID by using it and to see the output in the Picsimlab. The next, the softwares and hardwares I used in this internship is first the STM30 Cube ID to write, compile, and debug code. Picsimlab simulate STM32 qubit and Python at the develop AV dashboard. And the Pi serial UART communication between two STM30 and Python. Hardware is STM32 Blue Pill is the main microcontroller. The protocol is the communication in between UART, universal asynchronous receiver transmitter. The software used includes that is STM32 Cube is due to configure also peripherals like GPIO, UART, ADC, and the timers. On the hardware side, the STM32 Blue Pill microcontroller act as a central controller of the system, the main control. UART, Universal Asynchronous Receiver Transmit. Communication is used to transfer process data from STM32 and the Python. All these tools work together to create a complete embedded system. Next, I'll go to the embedded systems. An embedded system is a specialized computer system designed to perform a dedicated function with a larger system. Unlike personal computers, embedded systems are designed for specific application and operate high efficiency, reliability, and low power consumptions. An embedded system mainly consists of a microcontroller, sensors, actuators, memory, communication interfaces, and also the software. Uh, Today, embedded systems are used in various applications like automobiles, smartphones, washing machines, medical equipments, industrial automation, robotics, aerospace, and IoT, etc. In the automotive industry, embedded systems controls the engine management, braking systems, airbag deployment, The dashboard displays battery management and the driver assistance system. In this project, the STM32 microcontroller serves as the embedded system that continuously processes sensor value and update the dashboard. And next, STM32 Cube ID and Picsimlab. It these the tools I used to enter this internship. STM32 Cube ID is a official integrated development environment provided for STM32 microcontroller. It combines code editing, compiling, debugging, and firmware generation into one platform. Using STM32 Cube IDE, developers can configure peripherals like GPIO pins, all the pins configure it, and write embedded programs and debug the errors and upload firmware to the microcontroller. And the next, this the key features of this STM32 Cube IDE is a firmware flashing to STM32 boards. View it to STM32 board. The next, a Picsimlab. Picsimlab is an embedded system simulation software. The programmable IC simulator laboratory that allows us to simulate hardware without requiring a physical development board through UART communication, a universal asynchronous receiver transmitter communication. It supports STM32 Blue Pill boards and provides the inputs and outputs we require, like virtual LEDs, switches, potentiometers, sensors, LED display, and the UART communication. And advantages of this Picsimlab: it doesn't require physical hardware. It supports multiple microcontroller boards. It tests the UART communication. It debugs real-time errors. It validates the firmware very fast. And it is easy to integrate with STM32 projects or microcontrollers. Using simulation software reduce hardware cost and allows easy debugging before implementing the project on real hardware. And the next, the project introduction. I done in my complete internship a title electric vehicle dashboard and ADAS, a monitoring system. The objective of this project is to simulate an EV electric vehicle, a dashboard that displays important vehicle information in real time. The dashboard displays vehicle parameters such as speed, battery, percentage, a motor torque, temperature, a driving range, accelerator position, the brake status, and also the obstacle distance. The features of this project: it display speed like parameters, it gives warning messages, it accepts with UART communication, and finally display it in Python graphical dashboard. A need for the project: a smart dashboard improves the driving experience by presenting a real-time vehicle information clearly and providing timely alerts. And it gives the warning messages. The STM32 Blue Pill continuously reads sensors values, and also it processes the information using Emertxe and send the data through UART communication, universal Instant receiver and transmitter communication. The Python dashboard receives the serial data and it's display graphically the vehicle information. This project demonstrate the integration of embedded hardware with software visualization. A description is that the blue pill, it's microcontroller to generate vehicle parameters and transmit it to Python through UART, and the Python display it with real time. The next, EV and ADAS. Electric vehicles, commonly called as EVs, use electric motors powered by rechargeable batteries instead of petrol or diesel used. And it has many advantages, disadvantages, applications, uses. They reduce pollution, improve energy efficiency, reduce maintenance cost, and also support a sustainable transportation. They incorporate advanced electronic control systems to monitor the important vehicle parameters. These systems, electric vehicles, ensure efficient power management, improved vehicle performance, and enhanced reliability. Next, ADAS. ADAS stands for Advanced Driver Assistance Systems. ADAS is designed to improve driving safety by assisting the driver through intelligent monitoring systems. A common ADAS features include collision warning, obstacle detection, lane departure warning, blind spot monitoring, adaptive cruise control, and automatic emergency braking. The combination of these two represents the future of smart transportation, while the EV system focuses on efficient and environmental friendly mobility, and the ADAS, the various enhances safety and comfort driving confidence. Uh, Together, these technologies provide a real-time monitoring, intelligent decision support, improved energy management, and a safer driving experience, making modern electric vehicles more reliable, efficient, and user friendly. In my project, obstacle detection and warning indicators simulate basic ADAS functionality for improving driver awareness. This is all about EV and ADAS. Next, the project objectives and its system architecture. The main objective of this project is to create real-time EV dashboard. This dashboard capable of monitoring important vehicle parameters like speed, temperature, etc. Display that vehicle parameters on the Python GUI through which you auto communication. It gives alerts the system using Picsimlab. The system architecture begins with a simulated sensor inputs for the pixel. The STM32 Blue Pill read these analog values using ADC channel. This firmware it processes the data and calculate vehicle parameters like speed, etc. A UART communication, a universal assistant receiver transmitter communication, transfer the processed information to the Python application. Finally, the Python dashboard display all parameters graphically in real time. These architecture clearly demonstrate communication between embedded hardware and embedded software itself. The expected outcome from this project is a complete embedded system that simulates a EV dashboard, electric vehicle dashboard with real-time monitoring and it's the communication through UART. And the output will be shown in the Python GUI interface in real time. The next, a project overflow. Overflow is the project is about how it starts, the process, and how it ends. The workflow begins with sensor inputs from the simulation, means in Picsimlab. The STM32 continuously reads the analog values by initializing GPIO pins, UART, and a clock for reference. The firmware processes these values to calculate speed, battery percentage, temperature, torque, driving rate, and obstacle detections. Simply it generates vehicle parameters. The processed values are formatted into UART, Universal Listener Receiver Transmitter, messages and transmitted every second. The Python application receives the serial data, interrupts it, and update the graphical dashboard continuously. This process repeats throughout the execution of the project, providing live monitoring of the simulated electric vehicles. It starts, it initializes, it generates, it format it and send it to UART and UART send to Python dashboard. The Python display real-time dashboard that generate ADAS warnings and it also repeats. These are the complete workflow of this project, EV dashboard and the ADAS. Next, I will open my STM32 Cube IDE. These are the project I created, EV dash. The project name, it includes core files, include files, source files. For this project, I created some source and header files such as adas.h, foil.h, uartshell.h, ultrasonic.h, and also likewise that source files adas.c, a fault.c, uartshell.c, ultrasonic.c for my project requirement. And this is the main C code. I include my all header files. Main C code. Next, I will execute it, build a project. It shows Zero errors, zero warnings, successfully built. And here in debug, the binary file generated. And next, I will go this STM32 Cube IDE. Here the project folders. Here we develop the code, embedded C code, and build clean. For the generation of binary file, go to projects properties, C or C++ build settings, see post build outputs, convert to binary file. Then apply and close. It generates in debug core source. It will generate a binary ev dash binary file. And this is the configuration. The pins I configured. It opens. These are the pins. PB0, PB1 is per first ultrasonic sensor. 2, 3 is per second ultrasonic sensor. 4, 5 is for third ultrasonic sensors. And the PC13 is it's like a buzzer. These are the ADC and potentiometer channels PA0, PA1, PA2, PA3. These are the UART X receive transmitter. UART from communication between Python and STM32. And the PB8, PB9, PB10, and PD11 for LEDs. Alarms, like alarms. These are the pin out and configuration. I2C file is nothing but input and output configuration. Next, these are the clock configurations. RCC, that's 72 megahertz. I'm giving input 8 heads. Next, it multiplied with 9. It enables clock and gives 72 millihertz. These are the clock configurations. The pin in and out configurations. Next, we will move to build again. Main C. It builds with no errors, zero errors, zero warnings. And EV dash binary file is also executed. Build. The next, go to Picsimlab. These are the Picsimlab board. The microcontroller used in this is STM32F103 C86. The modules as spare parts. The tools, IO, virtual term, the file, the boards. It will restart a file, load binary file I created, ev dash binary file, and open it. Open modules and spare parts I created. This is the output. Here we see vehicle parameters like speed, SPOSI, temperature, its range, its alarms, ALM, its faults. A faults like ADAS parameter. It's a left distance, right distance, a front, left, right. First components, there is the potentiometer to read ADC values. This is the acceleration point. This is the brake point. It is SOC, state of charge, and it is the motor temperature. These three are ultrasonic sensor. It detects the vehicle obstacle. It is IO virtual term. It receives data. And this is alarms. It's continuously varying the data. I change the values will be changed. A front distance, a left distance, ultrasonics, a right distance. TTC, a time to collision, a collision, BSD blind spot, ALM alarm, it's fault. A first in front distance, the first fault, it's alarm. The number is 3. When the alarm is 3, the LED will be showing message. It's alert message. And this front for a red LED. And the next, a left distance. I change the values here, and here also the values changes. Likewise, I change the values here, it also changes here. Front left 400 time to collision. This is the fault. Fault number 3 is nothing but yellow. It motor temperature increases, fault will add. Motor temperature will decrease. The next right. These three alarms, yeah, like alert messages, like that. It's a fault LED. Here last is fault. It's number 2, fault LED. These are the buzzer. It's connect pin PC13 and the left distance. See the distance I'm varying. Here the also distance is also varying. Likewise, it gives alerts. Alerts. It's normal. Likewise, here also the distance will change. Its distance change. Next, I will move to a tool, a VSPE tool, the virtual serial port emulate. I created two ports. It's a pair port, common and comfort. Uh, I'll go to here, a virtual pair, and click next. Then here, a common. Yeah, I already configure it, so it's the common and comfort. I'm ready to use it. This tool, it passes the information in Picsimlab into the Python dashboard for varying the values in it. STM that and these all source files and header files to create a source file. Click source new, and a new source file, and name it. And also header file, new, and also header file, and name it and finish. Header files, IOC, Picsimlab. I reload it, EV dash, debug. This is actual process, EV dash. It's closes and open it, EV dash system, right? It gives alarms. Is acceleration point, brake point, SOC, motor temperature. Next, we will move to EV dashboard. The advisory is the warning. This changes according to my Picsimlab values. That is received in IO virtual term. There are the values here: the torque, acceleration, brake, motor temperature. The alarm is normal here. Next, I change the values. It gives different. It's changed the values. I'll change these values. It will changes likewise. The distance apart. Mode normal. Next, advisory. It gives alarm likewise. Here in a graphical mode, it is a real time showing. Fault, zero fault, zero, four fault is coming. LED we go. That this for blue. Left distance. This for alarm, right. This for gray. Advisory alarm. Here the LED is glow. Here shows advisory. So this is a message alert. It's normal condition. Normal. Motor temperature is high. It gives a fault. Here is normal. Is the acceleration. It is a distance. It changes like by it's these Picsimlab values. This is what I built project, and we'll move to and the next the applications and the future scope of this project. EV dash and a dashboard and ADAS. This project has several practical applications. It can be used in electric vehicles for real time dashboard monitoring, automotive research, embedded system education, prototype development, and the driver information systems. EV dashboard, automotive monitoring systems, driver information systems, embedded systems, and the simulation based training. In the future, the project can be enhanced by integrating GPS navigation, IoT connectivity like a Wi Fi, a cloud data storage, a mobile application, a battery management systems, a AI based driver assistance, and advanced ADAS, advanced resistance license system, features such as a detection, blind spot, traffic sign recognition, and automatic emergency brake. A GPS integration supports Bluetooth or Wi-Fi communication, connect vehicle sensors, cloud-based monitoring. These enhancements would make the system more intelligent and also the closer to modern automotive technologies. The applications and its future scope. Next, feedback and internship experience. This internship was highly valuable learning experience for me. It enhanced my understanding of embedded systems and gave me practical experience in embedded C programming, STM32 microcontrollers, development through UART communication and debugging it, and also the problem solving skills. I also improved my confidence in solving technical problems, the documenting projects, and presenting my work. The guidance provided by the trainers and mentors helped me develop both the technical and professional skills like how to build resume. And the internship provided valuable practical experience to understand embedded systems development process. It improved my technical knowledge, confidence, and ability to work on real world projects. Overall, this internship has strengthened my interest in embedded systems and automotive electronics, and also give the basic and the embedded systems, both software and the hardware. The next, I concluded this presentation with it. This internship provided me the practical knowledges. I understood how embedded hardware communicate with software to build real-time monitoring systems. The project enhanced my skills, the EV dashboard and ADAS project in STM32 programming, using microcontroller, UART communication, Python dashboard with system integration. This internship has motivated me to continue learning advanced embedded technologies and apply these skills in future projects and my professional career. Thank you, Emertxe Information Technologies. Thank you.